Welcome back. I think this slide might be where we left off. I don't remember. One thing I want to point out that I just realized is that I've rearranged these slides a bit, but I haven't changed the math or the numbers on any of them. And what that means is that the very last slide, which has the answers, has the wrong slide numbers. So there are three kind of questions in these slides that get answered on that last slide. The first one is this one. The second one is this one. And then there's one other, so you'll just have to figure it out through context clues. Good luck. Okay, so we are going to skip this slide. What I'm showing you here, if you go back and look at this data set, that data set, same data set, in microbiology, in the research community, we wouldn't graph it like this, we'd graph it like this. Instead of 10 to the third power and 10 to the fourth power, 10 to the fifth power, 10 to the sixth power, we actually take the logarithm of the data themselves so that anything that was worth 1,000 becomes 3, anything worth 10,000 becomes a 4. And this is really useful for doing statistics on numbers that span orders of magnitude. And so in my research, I had to do this all the time. But you don't have to. I just thought you should know if you ever see something like this. That's what it's about. All right, so what kind of math are we going to do? Well, one of them has to do with turbidity. Turbidity is the idea that as cells become abundant, they start to scatter light, and so the water they're in becomes cloudy. So if you give cells, if you fill a test tube, wow, why would I have left it like that? If you give cells a test tube full of water, and you fill it with, I don't know, some kind of nutritious liquid that is more or less yellow. What we could find is that one individual cell wouldn't look like much, but once you get a whole bunch of cells, they change the optical properties of the liquid. And we'll come back to like what this liquid would be. In lecture 3, we will talk about what we feed microorganisms and what they need. But for now, let's just think about what happens when they get what they need and they start to grow. So we start with one cell and it becomes many. What we find is that it starts to scatter light and become cloudy. When this happens, when it scatters light and becomes cloudy, we call it turbidity or cloudiness or optical density. And this is what makes milk look like milk. Little tiny particles scatter light. And I'm going to show you a little demonstration because we don't get so much time in our lab with liquid cultures early on. So I just want to show you in a different way what it looks like, and we can apply it to microorganisms. I want to show you this. I have a demonstration, sort of. Okay, hi. So this is a bottle I made a long time ago that has a rheoscopic fluid in it. And a rheoscopic fluid is made of little crystals that they kind of mimic what bacteria would do in water. And they're meant to make it, to make turbulence visible. So that's kind of what that does. And I only have it because it's cool. I mean, I don't need this for anything, but I keep it because it's cool. But it also mimics bacterial turbidity. And so I want to kind of show this to you because I've always had a lot of trouble helping students understand this. But let's say that there is a light source. It shines at you, it's very bright. And if this light shines at you and something passes in front of it that doesn't scatter much light, the amount of light doesn't change much. So it gets a little bit darker, but it stays pretty much the same. So at least it's supposed to. If I do it slowly, it gets a little darker. And then that's because some of the light is being scattered by this glass and by some of the dirt on this glass. Okay, so if we have something very turbid, it's going to scatter a lot of the light. And so if I shine this light at you, and I put this turbid thing between you and the light, it gets a lot darker, right? That light is much brighter than this. But because this is scattering the light, that light couldn't all get to you. A lot of it gets scattered in different directions. So that's what it would look like if it could get to you. That's what it looks like minus the light that gets scattered. So in terms of light getting scattered, this is a trick we use for seeing bacteria in test tubes. The idea is, if I shine the light from the side, if I shine it like this, the light isn't getting to you. If I hide it like that, it's not getting to you at all. Because it's pointing away from you, the light rays are going a different direction. But if I put something in front of it that scatters light, some of that light is going to get scattered at you. So this is going to light up, like so. And that's all light that's being scattered randomly towards you. That's what you're seeing. And if I take that away, the light disappears. So we use this trick in the laboratory to figure out whether cells are growing in our media or not. We hold it up to a light indirectly and see whether it glows. And that is what I'm showing on the next slide. So this is a picture of 4 test tubes that have microorganisms in them to different amounts. This one has the most microorganisms, this one has the smallest number. And there's a black background. So these are just test tubes with a little bit of broth and microorganisms. And there's a black background and they're lit from the side. So if this is kind of glowing, it's scattering light back at you because the little cells are scattering light and they're making it cloudy. And we can actually use this to estimate the numbers of cells. We use this as a handy way to track how fast they're growing. We just measure the turbidity, and that's an easy thing to do from a technology point of view. And where we come at this is that this tube that has clear liquid in it, no cloudiness, that doesn't mean it has 0 microorganisms. In fact, you can hide 10 to the 6th cells per milliliter Whoa, sorry everyone. Without causing any turbidity at all. Turbidity. Okay, so that's not legible because I'm switching from my big drawing pad to my small drawing pad. Sorry about that. But the point here is that you can hide 10 to the 6th cells in every milliliter of a nutrient broth without it looking turbid at all or cloudy at all. So what we can do with this, we can relate this to a volume of water we might know about. So what about a water bottle? How many cells could be hiding in your crystal clear water bottle? Well, a lot of water bottles I've seen hold 750 milliliters. And so if every one of those single milliliters has 10 to the 6th bacterial cells in it, it'll still be crystal clear. But how many would you be drinking if you drank the whole water bottle? How many bacterial cells would you be drinking? So we want to answer this in scientific notation. We want to have the right units. Let me show you how I would do this. So all I'm going to do is multiply these two numbers together. So I'm multiplying 10 to the 6th, and the units of that are cells per milliliter, and I'm multiplying that by 750 milliliters. All right, how do I approach this? How do I get the answer? And then how do I put it in scientific notation? Well, what I want to do is get everything into scientific notation as quickly as possible, because that makes it a lot easier to do this math. So this part is already in scientific notation, or almost. 10 to the 6 is equal to 1 times 10 to the 6th. And this is in scientific notation. So we can rewrite what we need to do here as 1 times 10 to the 6th, and that's in units of cells per milliliter. And we have to multiply that by 750 milliliters. Okay, let me show you how I would do this. The first thing I want to do is make sure I set up the math correctly, and to check that, I look at the units. So I have it set up as 10 to the 6th cells per milliliter times 750 milliliters. And the question I asked was how many cells can hide in a water bottle with a volume of 750 milliliters. So the answer should be some number in units of cells. And so is this set up correctly to get that? Well, what I want to do is see if I can cancel any units. And milliliters is on the bottom here. Milliliters is on the top over here, because remember, this number here, we could pretend it's divided by 1, so that wouldn't change it. And so milliliters is on the top and the bottom, which means we can cross out milliliters. And that leaves us with units of cells. So we know this is set up correctly. It's going to give us the right units. The question is then, how do we do this math? And what I'm going to do is convert both of these two things we have to multiply together. I'm going to convert them into scientific notation. So that's going to be my first step. So 10 to the 6th, to convert that into scientific notation, it's very close, because remember, scientific notation is always going to look like some integer, we'll call it x, times 10 to some power, p for power. I don't know what mathematicians would use here. Or it could be x point y times 10 to some power. So there's going to be an integer times 10 to some power. That's scientific notation. Or it can be an integer with a decimal point with other numbers times 10 to some power. That's scientific notation. So if I have a number like 10 to the 6th, that's very close to scientific notation, because 10 to the 6th is equal to 1 times 10 to the 6th. We can multiply anything by 1. And this is in scientific notation. Score for us. So that's the left part of that's the first thing we're multiplying. That's this part. Now I have it in scientific notation. 1 times 10 to the 6th power. So then how do I put 750 into scientific notation? Well, to put a number like this into scientific notation, I'm going to use a trick. I'm going to move a decimal point. So 750 has an implied decimal point after it. 750 is equal to 750.0. And so that shows me where this decimal point is. But that's not in scientific notation, because what I want is some number, some number times 10 to a power. And in this case, I'm going to want 2 digits. So it's going to be x point y times 10 to the p. So the questions we come up with are, what are the integers going to be and what's the power of 10? Well, what we do is we count how many times would we have to move this decimal point to make it look like scientific notation. And to make it look like scientific notation, I'm going to want it to be 7.5. So in order to make it 7.5, I have to move the decimal point 2 times. And if I do that, then I know that's my power of 10. So this becomes 7.5 times 10 to the second power. And if you don't believe me, get a calculator, multiply 10 to the second power, and then multiply it by 7.5, and you'll get 750. So that is in scientific notation. So now we have both of our pieces are in scientific notation. So now we're multiplying these two scientific notation numbers. We're multiplying 1 times 10 to the 6th times 7.5 times 10 to the second power. And the answer to that will be the number we're looking for in units of cells. So what can we do to get to that number? Well, the first thing I want to do is get rid of this 1. Because we're multiplying all this stuff by 1, we can ignore that. So we can rewrite it 10 to the 6th times 7.5 times 10 to the 2 cells. Now, again, I'm going to want this to be in scientific notation, so I'm going to want this integer stuff on the left. But we're still just multiplying them all together, so it doesn't matter what order they're in, so I can just rewrite it 7.5 times 10 to the 6th times 10 to the 2. And now it's very close to being scientific notation, because the answer is going to be 7.5 times 10 to some power. So here we have 7.5 times 10 to the 6th power, and then we multiply all that by 10 to the second power. So what do? We add these two exponents together. So we would end up with 7.5 times 10 to the 8th power. And that is going to be our answer in scientific notation in units of cells. So what is 7.5 times 10 to the 8th power? This is an interesting thing we can do also. We can find that number in decimal notation. 7.5 times 10 to the 8th. We're going to move the decimal point again. We're going to move it to the right 8 times. So I have my 7, my 5, move the decimal point. 1, 2, 3, 4, 5, 6, 7, 8. Decimal point. Now I have to add zeros, and then that's my decimal point. So that's 7, 5, 1, 2, 3, 4, 5, 6, 7 zeros. So what I tend to do is just start at the decimal point and count over and add commas. So I'm going to put a comma here and here. So I'm going to have 750, comma 000, comma 000, and that is 750 million. So it's 750 million cells could hide in a typical water bottle without changing the optical properties at all. So there you have that. And again, if you couldn't follow what I'm doing, I'm not a math teacher, so I really wouldn't be the person to ask about how to fix that. I would highly recommend looking up the videos for Khan Academy powers of 10 or scientific notation, because those are very clear and they're actual math teachers who know how to teach math. All I'm doing is showing you how I would do the calculation that's meant to be review, but if it's not, check out Khan Academy videos or whatever videos you prefer to use. All right, so there's one more thing I want to show you before I end this video, and that is what exponential growth is like from a human perspective. So if we go back to our slides, remember how we graphed a data set like this, and we saw this exponential curve, but if we use semi-log graphing, it becomes a straight line. Well, in our experience of living, we don't look at things with semi-log vision. This is how we experience our senses. So what do I mean by that? Well, exponential growth means that for a lot of exponential growth, we don't perceive any change. We don't perceive any evidence of growth. And then at some point, it's like a light switch going off. Suddenly, we perceive huge evidence of growth. And that's what we get if we inoculate cells into nutrient broth and let them grow for a long time. We see nothing. We see no change, even though they're doubling, because they're less than 10 to the 6 cells per milliliter. And then at some point, they get above 10 to the 6. They get up to 4 times 10 to the 6. That's 4 million, and then 8 million, and 16 million. Suddenly, they're way above the threshold of cloudiness. So they go from not cloudy to very cloudy incredibly quickly because they're growing exponentially. In the next video, we're going to look at the phases of growth as they happen in a test tube. So I will see you there.